Hi guys, so delighted to meet you. Adrian, obviously from Dublin, Ireland. Trying to give you guys a one-liner, and so advanced apologies for a bit of a goofy sort of definition. CS is kind of like a Siri for resumes. So we basically built a knowledge graph in recruitment, and we use that to train machines understand resumes. We deploy that kind of stuff for job boards, big recruitment agencies, that kind of stuff. So we're able to, say, power Monster.com and match all their candidates with all open positions based only on resume files, so Word documents, that kind of stuff. Right, so concretely, what is it that we do? 3 areas in particular. So resume parsing at scale. This involves, obviously, mostly I/O. How are we doing that? We're deploying a pipeline, an application, an AKA cluster application. Our workers are actually AKA camel actors, if you guys are familiar with camel, to enable integration with enterprise sort of data flows. We ingest files from all kinds of sources. So in our case, in our industry, we can find resumes on hard drives, on cloud, pretty much everywhere. So we actually, over email, by the way, really important. So we grab them from all over the place, and yeah, we parse them. Second thing that we do, information retrieval, so identifying patterns within structure and phrasing of resumes. So think linguistics right now, not necessarily words like TF, right? And match them with job descriptions automatically. We, of course, tap into external, as we analyze resumes, we tap into external sources of signaling, in our case, GitHub, which is really important. So when we detect GitHub links, we go and fetch repositories, actually, non-forked ones, so really source code, and then we grab all that kind of stuff, sample it, and expose it on the interface. We also tap into LinkedIn, all that kind of stuff. Based on that, we do real-time analytics. So we do salary recommendations, for one. So we mine 15 job boards currently. As we, each, I would say, fifth position has a salary published, right, in terms of minimum, maximum. So by analyzing all that kind of stuff and training a couple of regressions and translating that on top of resumes, we're forecasting salaries for candidates. The really cool part in this area is the fact that we forecast also skills, but we forecast skills that maximize a candidate's salary. So if we realize that you kind of like have a background in Java, that kind of stuff, we probably will recommend you Clojure or Scala or things like that, because that will maximize your salary. Of course, like we have lots of similarity between candidates, search with job descriptions, all that kind of stuff. Right, so first of all, we don't actually have that many rights, but when they arrive, they actually arrive in the order of millions. So see this in terms of a recruitment agency having to ingest all their current database, which are only files, really. So what do we do in order not to go down when we hit a spike of, say, like lots of data? We actually push that directly onto S3 from web, from everywhere. And after that, we start batching. We have, so I will actually talk about the whole end-to-end pipeline, which includes front-end interactions, backend, which is Node.js. We use that only to bridge requests, and then obviously the AKA, our AKA application, and everything gets stored into Couchbase. So, and by the way, everything is immutable. Right, so in our case, I was saying everything is pretty much a stream. So we start basically with documents. We have an agnostic agnostic transport on front end, reaching back end, which in our case currently it's a WebSocket or Ajax. We reach Node. From Node, we basically start querying our internal pipelines, and that's happening in our case. We also are transport agnostic on that end, in the sense that we would actually had transport like Kafka, HTTP, 0MQ we were playing with, and all that kind of stuff. We enter an akka streams pipeline, which starts doing lots of flat maps and all that kind of stuff. And we output basically at the final end the JSON data structure. Right, so not to, this is some sort of a pseudocode, probably a bit small, the text. But in big lines, what it describes is actually, first step. So as somebody uploads something over cloud, we basically only need to download that, currently S3. We get back a byte array output. Then we do conversion. In our case, conversion is performed by a Mesos cluster. So some Docker containers deployed over a Mesos cluster. All the conversion is actually in memory. So I will insist over that. Then we really start parsing. We convert everything to PDF. We use PDF box. We perform a bit of named entity extraction, tokenization, regex, vectors, all that kind of stuff. Then we proceed with lots of context. So extracting context, in our case, education, for instance, that's Elasticsearch. So in our case, currently, we use percolation. So because universities, we know which the world universities are. What we do, basically, we fed that to Elasticsearch, and we do an inverted sort of search, which is pretty fast, okay? Then we also do, when we detect a resume, we do lots of I/O. So if we detect portfolios, we go and actually screenshot those ones. If we detect, I was saying, GitHub links and things like that, we go and fetch source code. All that kind of stuff, it's managed by akka streams. I will actually talk about that. And in particular, we love the akka DSL. The fact that we can actually broadcast flows, and we can schedule, I/O sort of flows one way, all the logic on the other way, and all that. After that, we have a series of AI calls. So mostly regressions, maybe some interactions with some TensorFlow models. Then we need to make sure that we can actually kill this stuff. So it's basically passing through a shared kill switch. And in our case, all the monitoring, basically, all the instrumentation, all that kind of stuff, we use Prometheus. Like, it's an excellent thing. We collect data from Node, from Scala, pretty much all over the place, and the systems as well. When everything is complete, basically, we return an HTTP response. So all this kind of stuff is pretty much one click. So it's one request, really. Right, so as I was explaining, basically, we actually have a pool of workers, business logic, all that kind of stuff. Traffic arrives onto S3, we start an task orchestration, and then everything is pretty much on a single stream. Right, I will actually explain right now how do internal workers, how do they look, basically. So what we have in here, we have a series of workers. A worker actually in our case means a producer and a consumer. Producer in the sense that we want to keep them agnostic, as I was saying. And that producer in our case, that's the akka camel actor. Executors all have access, read access to Hazelcast. So just not to, to have to tap into data if we need it. Most often we don't, but there is a Hazelcast layer on top of it. And as data stores, basically we use Couchbase, it's immutable, which auto-replicates XDRC to Elasticsearch. We do some really, really cool stuff at this end, and I will insist over that at the end. Right, so I/O. How do we do I/O currently? We deploy Docker containers. What do they contain? It's basically simple Golang web servers written like we use Iris framework, I believe. And that's an example of a simple conversion. So what do? We actually mount a run disk in the Docker container. We use LibreOffice, and basically when a request arrives, we just simply, execute that stuff onto RAM disk and then return the answer back. How we deploy this kind of stuff at scale? We have another container in the system that's subscribed to a marathon event stream. And upon doing the health checks, it pushes all the correct, all the instances, all the IPs and all that kind of stuff into console. And from console, we actually have a load balancer, HTTP load balancer, which is Fabio, written in Go, that simply checks up console and updates a routing table. So therefore, we're actually able to tap into any of those containers via simple HTTP requests. Everything is basically routed via Nginx on some port, and the request, really, the I/O conversion, is for us, it's like something like this. So it's basically a request, and marshal the response, and what you get back is an byte array. That happens with both documents, or Word documents, or PDFs, or zip files. So if we have many files, maybe in a zipped, we also perform conversion in memory. Deflation in memory, sorry. Right, so how do interactions work? So we have, obviously, the front end. In our case, if you guys are familiar with React, all that kind of stuff, so we have React view layer. We also have a data layer, Baobab, currently. So it's a state tree. It contains all our front-end states in one tree, lazy computation, all that kind of stuff. And all interactions are managed by Cerebral. See it as a state controller. The beautiful thing about this guy is the fact that it actually allows you to decouple both the view and the modal. So in our case, React can actually become Angular really quick. We don't necessarily need to do that. Or for high performance, if you guys are familiar with React, you also have a drop-in like Inferno. The other side, so the data part, the model part, it's actually we actually were toying with immutable JS, all that kind of stuff. So it's a simple data tree. Right. What goes on, as I was explaining, we actually are performing a request. It arrives by Node.js, sees the futures in there, and then a response back. Right, so in our case, I was explaining that one worker, in our case, is composed by a producer and a consumer. So the consumer, so this is the Hazelcast layer, the read memory layer. We also have a near cache, I think cache to K or something like that. And this is the producer that we have a series of threads. They could actually consume data from Kafka, or currently it's mostly HTTP, Akka HTTP, but yeah. Why do we have this kind of setup? So we basically don't want to overload executors. So the smallest parts of work, in our case, this kind of stuff, we don't want to make them aware of curve context and communication, all that kind of stuff. And yeah, basically it allows us to maintain like really pure functions as small and as focused as possible. Scale, of course, like we are using round robin from Akka. We are using Akka cluster to scale horizontally. Isolated the actor system, so pretty much no one, everything is location transparent, all that kind of stuff. Right, so what's about Couchbase? So if you guys, I'm not sure if you guys are familiar with it or not. In our case, that's an immutable database. So basically, there's no updates in place. It's only inserts. What this means for us is the fact that we can actually get free analytics of that, because you always have a previous sort of data which you can tap into. Also, Couchbase, the difference between CouchDB for the ones of you that are familiar with it, and Couchbase, actually another layer which is man-based, like man-cache sort of thing. We keep them all in the same system. Why do we do that? Because if we actually want to tap into, to interact with other systems, we would like to be kind of like, flexible enough to interact with different other sessions from PHP or things like that, which usually use man-cached. Right, Elasticsearch. So, obviously, the classical case for search on Elasticsearch is, search. So we're not returning full documents, we're only returning document keys, and then we fetch that from the key value stored from Couchbase. I was saying also Elastic percolations or inverted search. We have universities in university names. We search with a raw text and we get back really the matching universities in text. Right, so why Kafka in a pipeline? So we do that in order to do logging, not to do asynchronous logging, obviously, and job recovery. So basically, we don't really want to lose candidates, right? So that's really important. So if we fail, we want to be able to know what kind of data fails, so to be able to sort of reschedule, restart. I was explaining when we receive uploads, we receive uploads from multiple sources. So in our case, batch. We have cross-platform application as well, allowing resume ingestion, Mac OS and Windows, mail, web, that kind of stuff. The flow I was explaining, it's basically we send everything to S3 and then we batch afterwards. And I'll get a bit into AI right now. So in our case, we do, we write software for recruitment. We're not recruiters ourselves. So we actually need to adapt. We considered it a really wise decision to actually define AI as parts industry-specific data and parts sort of generic linguistics matching. So for IT, in our case, so we maintain basically two vectors describing each document, right? An industry-specific vector, which is in case of IT, we define that ourselves, and we had no problem with that. As software development, web design, data science, stuff that people can actually relate to. So it's an industry-specific topic vector. And by the way, we were assessing lots of ways on how to generate those kind of vectors. In our case, we don't use classifiers at all. So it doesn't really work, doing skills and abilities for that. So we actually, feature engineering is crucial in this kind of case. And in our case, the topic vector for IT, it's like 11, all the topic vectors are 11 elements. So it's like a really small vector. But those 11 elements in that vector are regressions, all of them. Also, we also maintain an document vector. So this is in the space of linguistics. For the ones of you familiar with Word2Vec, that kind of stuff, so we map everything onto a knowledge sphere, right? And in our case, those are high dense vectors. In our case, 300 elements within a semantic space. I have a couple of visualizations. I have them live as well. So we're actually, when we're talking semantics, we are for data science, that's what you pretty much want to see, not islands, not things like that. So a really nice, neat area describing the document. So in this case, the resume, it's leaning towards data science, that kind of stuff. In this case, we actually, it's not really visible. We are analyzing what kind of information, meaning, generated towards that document vectors, contributed towards that document vector's contribution. How do we do similarity? So in our case, we have lots of similarities, industry-specific use cases. In case of IBM, let's say, they have 100,000 employees, and they want to, form a next best team around, a particular set of job descriptions. So those job descriptions, of course, are defined as well by vectors. And in this case, basically similarity, it's pretty much cosine similarity or dot product. In case of topic vectors, yeah, it's mostly supervised. Yeah, so we maintain glossaries. In case of document vectors, obviously unsupervised. How we do actually the document vectors? I won't insist much, but it's actually a process where we, first of all, we know what the topic space is. We do SVD just to, for a particular purpose. So as we analyze the resume, we cluster all the information in that resume via k-means. So the problem in k-means, as you may well be aware of, is actually the k, the number of clusters, right? So what do we do about that in order not to go blindly? We basically do SVD, figure out what the principal elements are. We kind of like strip out information, and then we actually find the k. That's the only purpose why we use SVD for. Once we have the number of clusters, we cluster things. We employ our own glossaries to further filter out irrelevant clusters. And then we have our own sort of BL to compute the document vectors from those kind of clusters.
Is that better than doing a hierarchical clustering?
Sorry?
Was that better than doing a hierarchical clustering on the k-means and then just choosing by some of the gap in the datagram?
So to be honest, we were looking currently on that sort of side. It's, lots of ways. We were looking at probability distributions, HDP, by the way, like hierarchical distributions, or it worked for us. We have a bit of a problem in the sense that it's still not perfect. So our current area of research is not only defining a document by one vector, we actually want to define a document by 4 vectors. So in our case, something like Java, Scala, that kind of area, and then business marketing, which is a different sort of thing. And then use something like words mover distance, but it's a bit slow if you.
Maybe look at like doing your LDA hierarchical. So at a low level and then
hierarchical declared
where the next level is a hierarchy of the LDA topics below it.
Yeah, so this is under constant research for us currently. Yeah, right. So all the similarity, as I was saying, we are performing via cosine similarity. If we actually have a really large number of documents, we use Annoy from Spotify, an excellent project. That currently has bindings for Python and Java, from what I'm aware of. Sorry if I may be wrong somehow.
So what is the document size you deal with? How many documents do you have?
Sorry?
What is the document size you deal with? How many resumes do you have?
It depends from customer to customer. So we cater to recruitment agencies, right? So we don't, when we're talking of a pool of candidates, of course we don't open up. So everybody is like kind of isolating their own space. So if we're powering Jobs.ai, you won't get to see us. So we're underneath, right? We don't even, everything is pretty much bound, confidential, even, all the data, all that kind of stuff. Right, so I was saying again, salary forecast. I already explained that, I believe. So by mining that kind of stuff, we realize how valuable skills are. We denoise lots of stuff, and then we translate that space into resumes, and that's how we actually forecast salaries. This is a really interesting use case, actually. So, mining. We start mining with a simple Python process, Scrapey, basically running on cron. Nothing really complicated. We fetch the data into Couchbase. From Couchbase, it auto-replicates into Elasticsearch. But on the Elasticsearch side, we actually have a small plugin which tries to figure out, right, so is this document parsed or not? And if it's not, it just triggers a small async message over Kafka, or somewhere internally, and a series of processes will actually pick up the document, this document ID, will do all the AI, and then will rewrite to Couchbase, which auto-replicates to Elasticsearch. So for us, what this translates to actually is it's actually free sort of interaction, if you will. So we just have to write data into Couchbase and call it a day. So we don't really need to do anything afterwards, because I think that after it's scheduled by that sort of round pipeline. Front-end. So, as I was saying, we employ React.js for Vue. I have an example of an import from Dropbox currently. It's basically a simple WebSocket message or Ajax message, bridged by Node, arriving into an Akka streams pipeline, and once that's finished, we send a message back with a confirmation. That's pretty much it. So it works exactly the same in case of 1,000 to 1 million files as it were for one single file. Right, so as I was saying, all the state is a unified JSON state in front end, controlled by Cerebral. Vue currently React. Baobab.js, which has cursors which are, I would say, cursors, right? So elements within the tree, basically. Lazy state computation, so whenever you're changing something in the state tree, everything else recomputes as you use it. Cached, all that kind of stuff. I was saying, industry topic vector, so this is where you actually can see one. So in our case, we have actually 11 categories on bottom, and then you have a quick heat map of candidates' abilities. When we talk about IT, we're actually talking, in this case, of data science, web probably it's at 100%, and software development. So for you to have a quick overview. Interactions, so basically it's on the front-end side, it's kind of like the same thing as you'd imagine on happening on Akka streams. I was explaining the whole information flow. Batch and scale. So we provide the cross-platform applications, as I was saying, that simply allows our customers to ingest folders of files. So in case of recruitment agencies, everybody has files all over the place, hard drives and all that kind of stuff. We just give them an application allowing them to browse for a folder and ingest that. Container I/O. So as I was saying, we maintain a series of Docker containers. So in our case, for conversion, doc to PDF, PDF to images, so utilities really. Inside, they do have web servers written in Golang. We also have a container which subscribes to the Marathon event stream. Whenever something happens to some of those containers, this guy will update the console. Will update console, and then Fabio will actually figure out which are the healthy services and then expose them as HTTP. For us, monitoring instrumentation is all Prometheus, Grafana, all that kind of stuff. Node and Java clients. For systems, we use a Node exporter from Prometheus. For Couchbase, to monitor Couchbase, we use Telegraph plugin. Alerting, when something happens, we use Alert Manager for that. So we use basically a couple of dashboards holding everything together. So both systems and performance and SLA, all that kind of stuff. Thank you so much. I will try to pick up on a couple of questions if you want afterwards. Yeah.
How do you deal with changing buzzword frequency? Do you retrain your word to back every 6 months or year? Or?
Usually don't need to, because once you mine it, you kind of like have an idea on the glossary. If we detect such things, we definitely do. But we didn't see the case actually, the need for that.
Okay, so it's not much of a non-station.
No, it's actually in our case when we compute all the document vectors, we know what skills mean, all that kind of stuff. So we don't really need to actually.
Cool. Well, I thank you for coming up here and
Thank you so much.
to us. Unfortunately, we're out of time for questions at this point, but we need to get the room set up for the next panel discussion here real quickly. So hang tight with us, and we'll be back online here in a second. Thanks a lot, Adrian.
Thanks, Amir. Cheers.